Welcome back. This is our fifth deep dive into flight safety analysis, and today we're getting into something really fundamental.
We're tackling trajectory analysis for normal flight.
Right. So basically, how do mission planners figure out exactly where a launch vehicle is supposed to go during a typical flight? Not just one line, right, but sort of the expected corridor.
Exactly that. It's a peek behind the curtain at planning safe launch and reentry. And we've got some solid sources to guide us.
Yeah, let's mention those. We're looking at the FAA regulations, specifically 14 CFR 450.117.
And the advisory circular that goes with it, AC 450.117, which gives guidance on how to meet those rules.
Plus, we'll pull in relevant bits from the Part 450 Final Rule Preamble.
And the streamlined launch and reentry requirements, focusing just on the parts about this section, 450.117.
Okay, so our mission today, let's really unpack what trajectory analysis for normal flight means, why it's so critical for the whole flight safety analysis, or FSA.
It's about understanding that planned path, but crucially, also the normal variations we expect around it.
Good point. Okay, let's start there. What defines normal flight or nominal flight in this context?
Well, at its heart, nominal means everything's performing just as expected. Your aerodynamics match predictions.
Okay.
All your systems, internal and external, are working correctly. Engines are giving the planned thrust.
And things like staging happen right on schedule.
Exactly. Stage separation, payload deployment, all happening when they're supposed to. It's the ideal flight plan.
The perfect scenario. But I mean, reality isn't always perfect, is it? Even on a good day, how does the analysis handle that?
That's absolutely key. It's not just one rigid line. The analysis must account for expected variability and uncertainty, even during normal operations.
So it builds in some wiggle room.
You could say that.
Yeah.
Operators don't just model one trajectory, they develop multiple sets.
Multiple sets. Why? What do they show?
Well, first you have the nominal trajectory itself,
Okay.
the baseline. Then you have sets, showing variations due to expected performance differences. Maybe an engine gives slightly more or less thrust, but still within its allowed tolerance.
Ah, okay. Like manufacturing tolerances kind of thing.
Precisely. Or slight differences in how the vehicle actually behaves aerodynamically compared to the computer models. Minor stuff, but you account for it.
Makes sense. So performance variations, what else?
Uncertainties, and this is a big one. The regulations really point to atmospheric conditions, especially winds.
Winds, yeah. Always a factor.
Predicting upper-level winds perfectly is, well, it's extremely challenging. So the analysis has to include a range of possible wind conditions the vehicle might fly through.
And I guess other atmospheric things could matter too, like density or humidity.
For some vehicles, yes. Depending on how sensitive the design is, you might also need to factor in uncertainties in air density, humidity, maybe even temperature.
So you end up with this bundle of trajectories representing the spectrum of normal.
Exactly. It's about defining that operational envelope for a successful flight. This detailed upfront work is really the foundation for making safety decisions later on.
Okay, we've got a handle on what normal flight analysis is. How does it fit into the bigger picture, the overall flight safety analysis?
It's step one, really. The foundation. Remember, the FSA covers the whole mission.
Right, liftoff through, what was it, orbital insertion for orbital flights?
Correct, and including all planned component impacts or landings. For suborbital, it's the whole flight until everything is safely down.
Gotcha.
This normal trajectory analysis provides that predicted path for all of those phases.
So it paints the picture of success. How does knowing that picture help keep things safe during the actual flight?
Because it's the benchmark. Knowing where the vehicle should be is fundamental for developing hazard controls.
You mean to spot when things go wrong?
Exactly. If you don't know the expected path and its normal variations, how can you identify a deviation that might be hazardous? You compare real-time data against this analyzed normal corridor.
So it lets you see anomalies quickly. Does this connect back to the hazard analysis done earlier in the process?
Directly. Think about the functional hazard analysis. That's where you identify potential system failures and their consequences. The normal trajectory analysis gives you the context. How might that specific failure affect the flight path compared to where it should be going?
Okay, I see the link. And I'm guessing this expected path also helps define, like, the safety boundaries.
Precisely. The normal trajectory data, including those variations and uncertainties we talked about, is a primary input for setting the flight safety limits. These are the predefined boundaries in the sky or in performance parameters.
The sort of invisible fences
Kind of. If the vehicle goes way off its normal course and crosses one of these limits,
Action time.
it can trigger pre-planned actions. That might, in some cases, involve activating a flight safety system, like a flight termination system.
Okay, so the normal analysis tells you where to put those fences. Now, we've been talking normal. How does this relate to analyzing actual malfunctions?
Good question. That brings in malfunction trajectory analysis.
Hmm.
While normal analysis looks at expected behavior and minor variations,
Mm-hmm.
malfunction analysis looks at what happens when things go significantly wrong. System failures, unexpected events.
A different beast entirely.
Yes, but it builds directly on the normal analysis.
Mm.
The regulation for malfunction analysis specifically says it has to consider deviations from the normal trajectory.
Ah, so you need the normal baseline to even start analyzing the abnormal.
Absolutely. You need to know what right looks like to understand wrong. It also considers the limits of what might still be a useful mission, even if something hasn't gone perfectly.
Okay. So this normal data isn't just for setting limits and comparing malfunctions. Does it feed into other safety checks too?
Oh, definitely. Think about debris analysis.
Debris, even on a normal flight.
Sure, you have planned events,
Yeah.
like separating stages or deploying a payload fairing. These can create debris even when everything works perfectly.
Right, discarded hardware.
Knowing the normal flight path helps predict where that planned separation debris is likely to fall.
Okay, that makes sense. What about managing the airspace and ground areas?
That ties into flight hazard area analysis. The normal trajectory data helps define the zones on the ground or in the air that could potentially be affected during a routine flight.
Including those planned jettison points.
Yes, this info is crucial for setting up safety zones, issuing notices to pilots or mariners, and keeping the public clear of any potential hazards, even expected ones.
So the normal impact estimates are key inputs there. You mentioned winds being a big uncertainty driver earlier. How does the analysis use wind information specifically?
Well, because the normal trajectory analysis includes that range of expected wind conditions,
Yeah.
it supports something called wind weighting. This is where, close to launch, you use real-time wind measurements to make slight adjustments.
Adjustments to the trajectory.
Within the pre-analyzed normal boundaries, yes. It's like fine-tuning the aim based on the actual conditions rather than just the average or predicted ones to maintain safety margins.
Ah, like a golfer adjusting for the wind.
That's a great analogy. You have your intended swing, but you adjust slightly based on the wind you actually feel. And this all feeds into the flight commit criteria.
The go-no-go decisions.
Exactly. Those criteria are based heavily on the pre-flight analysis, including whether the observed conditions, like winds, fall within the range considered acceptable and analyzed as normal.
So it's not just theoretical planning, it's actively used right up to launch. Given all this complexity, how rigid is the process? Is there only one way to do this analysis?
Actually, no. While the regulation sets the requirement you must do this analysis, the advisory circular provides guidance on acceptable methods.
So there's flexibility.
Yes, it allows operators to use approaches that make sense for their specific vehicle, their mission type, the launch site environment. It's not a strict one-size-fits-all recipe.
That seems sensible. Allows for innovation, but keeps the safety goal central. Okay, let's wrap this section up. What's the main takeaway? Does doing all this guarantee a perfect mission?
Look, no analysis can promise a 100% guarantee in spaceflight. There are always unknowns.
Right.
But a thorough, well-executed trajectory analysis for normal flight is absolutely essential. It provides that foundational understanding of expected behavior
It tells you what should happen.
and the normal range around that, which then lets you identify deviations and have safety measures in place.
Yeah.
It's about building safety based on rigorous understanding of the plan.
So it's the indispensable first step. You can't really ensure safety without first defining what normal and safe looks like for the intended flight path.
Couldn't have said it better myself.
Well, thanks. This has been really illuminating. It definitely gives you a new appreciation for the sheer amount of work behind even a routine launch.
My pleasure. It really does highlight the meticulous planning involved.
And for you listening, we hope this deep dive into normal trajectory analysis makes clear just how critical this step is. Think about it next time you see a launch, all the complex calculations defining that expected path, all designed to keep everyone safe. Join us next time as we build on this and look at another piece of the flight safety analysis puzzle.